Hello students, welcome back to next session. So here it is ammonia hydrogen absorption system. So this is another type of refrigeration system. It is also a type of vapor absorption system. We will see in detail. So these are the topics in this unit. We have all these topics. We are going to see all these topics. And today we will complete the vapor absorption system. In this session we will complete the vapor absorption system, so that is known as Electrolux refrigerator. It is also known as ammonia hydrogen absorption system. So the domestic Electrolux, it is ammonia hydrogen refrigerator. So this is the block diagram of this type of refrigerator. Here we have a absorber. It is this is the absorber, and this is the hydrogen. Hydrogen and ammonia is circulated through evaporator and absorber, and here heat exchanger. Heat exchanger. So this is the heat generator. This is gas burner, and we have rectifier and condenser, and liquid ammonia is sent to evaporator, and hydrogen is supplied from absorber. So from absorber the hydrogen is liberated or generated, and that is sent to evaporator. So ammonia and hydrogen is coming together, and that is coming to absorber. Again that becomes a strong solution. Through heat exchanger it goes to, through generator goes to rectifier. So then it goes to the condenser. So finally condenser receives it. So ammonia vapors enters the condensers. So this is how the cyclic process taking place here. We will see in detail. And the domestic absorption type refrigerator was first invented by two Swedish engineers. They are Karl Munters and Balzer Van Platten, Balzer Van Platten in 1925 itself. So in that year it was found by these two scientists. So they were students at Royal Institute of Technology in Stockholm. So this is the idea was first developed by the Electrolux company of Luton, England. So that is why it is called as Electrolux refrigerator. So this type of refrigerator is known as three fluid absorption system. So it is also called as three fluid absorption system. So students, in your exam, if you find domestic Electrolux question, please answer this. Or if you find ammonia hydrogen refrigerator, you have to answer the same answer. And if you find three fluid absorption system, there also you have to write the same answer. So you have to be careful with these names, don't get confused, and write the precise answer. So key components here: ammonia vapors. The ammonia vapors circulate through the system, and generator contains ammonia and hydrogen, and rectifier, a device for separating water vapor from ammonia vapors, and then the condenser cools ammonia vapor into liquid ammonia. Evaporator uses liquid ammonia to absorb heat from the refrigerated space. Absorber, where ammonia vapor and hydrogen are combined with water to form a solution. So gas burner, so it provides the heat required for the ammonia and hydrogen mixture. So we have last heat exchanger. It facilitates heat transfer in the system. So these are the major components of the Electrolux refrigerator. So flow of fluids: ammonia vapors from the generator are directed through the system, starting at the rectifier, passing through the condenser, and finally reaching the evaporator. Ammonia and hydrogen mixture is passed to the absorber, where absorption into water occurs. The cycle is completed by circulating fluids that are driven by gas burners and gravity. So working principle here: the main goal of this system is to eliminate moving parts, making the machine operate without a pump. So the three fluids used are ammonia. It serves as the refrigerant due to the favorable properties of heat absorption, and hydrogen. So these are the two fluids used. So hydrogen is used to assist in increasing the rate of evaporation of liquid ammonia and is non-corrosive. Water is used for absorption purpose to absorb ammonia vapor and complete the cycle. So these are the liquids, these are the fluids used, three fluids. So that is why it is also known as three fluid system, refrigeration system. The ammonia vapors are absorbed by water in the absorber. The hydrogen gas, being the lightest gas, helps to increase the evaporation rate of the ammonia from the liquid phase. As hydrogen is non-corrosive, it remains unaffected in the process. So hydrogen is non-corrosive, so that is the best property we can have from hydrogen. The heat removed by the weak solution flows into the generator, raising the temperature of the solution, which aids in transferring the heat. The ammonia vapors are first passed through the external cooling source, where the liquid refrigerant undergoes cooling in the condenser. So gravity aids in the moving the refrigerant towards the evaporator, where the liquid ammonia is evaporated. The ammonia vapor is then passed to the absorber, where it absorbs the vapor. This cycle continues indefinitely as long as heat is applied to the generator. So evaporation of liquid ammonia. The evaporation is crucial for cooling, and it is accelerated by the hydrogen gas in the system. The lighter gas, hydrogen, promotes faster evaporation, resulting in more effective refrigeration system. So cooling in the condenser taking place, and the ammonia vapors in the condenser are cooled using an external cooling source. Liquid ammonia is formed here and passes to the evaporator. Water absorption process. The mixture of ammonia vapor and hydrogen reaches the absorber, and the ammonia is absorbed into water, while hydrogen gas moves to top of the absorber. The solution is then sent to the evaporator for cooling. So these are the key considerations of the system. So coefficient of performance, so that is COP, the coefficient of performance of the refrigeration system is calculated as the COP equal to heat absorbed in the evaporator divided by heat supplied in the generator. This formula highlights the efficiency of the system in terms of heat exchange, where the ratio of the heat absorbed versus heat supplied determines the performance. So you please remember these points, and the hydrogen gas circulates only between the absorber and the evaporator. So hydrogen is used between these two only. Please remember this. The entire process relies on the gravity flow of the refrigerator, making it low power passive system. So no external power is required to drive this system. The system is not suited for industrial purposes, as its coefficient of performance is low compared to other refrigeration methods. The Electrolux ammonia hydrogen refrigerator is a non-mechanical passive refrigeration system that relies on absorption and gravity flow. So although effective for domestic use, it is not suitable for industrial refrigeration due to its relatively low performance. So we see one more problem on this, that is the total pressure maintained in the Electrolux refrigerator is 14.71 bar. The temperature obtained in the generator is 418.7 Kelvin. To dissociate the vapor of ammonia and 1464.4 kilojoules per kg for increasing the total enthalpy of ammonia. The enthalpy of NH3 entering the evaporator is 335 kilojoules per kg. Take the following properties of ammonia at minus 15 degree Celsius. So here, this, if it is not given, you have to get it from the refrigeration chart. So that is pressure equal to 2.45 bar, enthalpy H1 of NH3 vapor is 1666 kilojoules per kg. Specific volume is equal to V equal to 0.5 meter cube per kg. The hydrogen enters the evaporator at 25 degrees Celsius. The gas constant for hydrogen is equal to 4.218 kilojoules per kg degree Celsius. Please remember this value, students, for hydrogen. Otherwise, it will be available in your these tables. And the specific volume of the hydrogen equal to 0.5 meter cube per kg, and H2 at 25 degree Celsius. Find the COP of performance of the system. Assume NH3 leaves the evaporator in saturated condition at minus 15 degree Celsius. So this is the uh, complete problem statement. You have to find the coefficient of performance of the system. So given data, first list down all the given data. So pressure equal to 14.71 bar, TE equal to minus 15 degrees Celsius, and TG equal to 15 degrees Celsius, that is generator temperature, and TE is evaporator temperature. T1 equal to 418.7 Kelvin, temperature of the ammonia in the generator. Enthalpy of NH3 entering the evaporator, that is equal to 335 kilojoules per kg. Enthalpy of NH3 vapor equal to 1666 kilojoules per kg. The hydrogen gas enters at 25 degrees Celsius, and gas constant is also given, and the specific volume at temperature 25 degrees Celsius are also given in the problem. So first list down all this and then start your problem. So this is how it is happening. So this is the evaporator, the first stage. First stage, NH3 is entering the evaporator and H2 is entering the evaporator, and NH3 plus H2, so that is 1 kg plus m kg. So that is the output from the evaporator. So calculation of pressure of hydrogen H2 using the equation. Using the equation of the state of the hydrogen gas, so that is that pH equal to RT by V. So substituting the known values, so pH equal to 4.218 into 258 divided by 0.5, so that is equal to 1226 kilonewton per meter square, so that is equal to 1.226 megapascals. So for calculation of the evaporator, so from this figure, so the calculation of the flow of hydrogen gas is done as follows. So PR equal to 14.71, V specific volume equal to 0.5 meter cube per kg, and T equal to 25 degrees Celsius. Using the specific gas constant of hydrogen R equal to 4.218 kilojoules per kg degree Celsius, we can calculate the total flow through the system. So volume of gas, hydrogen gas, the volume of 1 kg of hydrogen is in the evaporator is given by M equal to PHV divided by RT equal to 1226 into 0.5 divided by 4.218 into 258, that is equal to 0.5633 kg. Energy balance. So use energy balance for the evaporator. Energy balance, the energy balance equation is given by H2 minus H1 equal to Cp into MT2 by T2 minus T1 plus QE. So where H1 and H2 are enthalpy values for ammonia at the evaporator entry and exit respectively. So Cp is the specific heat of ammonia, and m is the mass flow rate of ammonia, and T2 and T1 are the respective temperatures. So substituting these values into the equation, 1666 minus 335, so equal to, so in terms of QE, we can find out this. So QE is given by, that is 1043 kilojoules per kg of NH3. So this is QE. And now coefficient of performance. So we know now all the values. COP equal to QE by QG. So QG is the heat supplied to the generator. So that is 1884.1 kilojoules per kg of NH3. So this is the given data. and substituting these values. So already we have found QE in the earlier slide. So that is equal to 1043 divided by 1884.1 equal to 0.5536. So this is the final answer, and COP of the system is 0.5536. Even though it is low, normally vapor absorption systems COP is lesser than the vapor compression systems. So this is the final answer, and this is the final topic in the vapor absorption system, and we stop the vapor absorption system. So in other type of refrigeration systems, we will see in coming sessions. In next session we will start the absorption cooling systems. So cooling systems, that is again a simple topic, we can complete in a very smaller duration of time. Thank you, students. We stop here, and these are the answers. And now you can see the textbooks and reference books. Please refer Kurmi for this, and this is in simple way he has explained. And CP Arora and Rajput also you can refer. And these other two textbooks you can refer. We stop here, students. We will again meet in next session. Thank you. Thank you, students.